Welcome to the information platform of WPsoft GmbH. Today, I'll explain why simulation software provides a superior method for comparing heat pumps compared to the ERP label. Heat pump selection software is becoming increasingly available in the market. I'll demonstrate the different types of software commonly used and highlight the distinct advantages that simulation offers over traditional methods. The most commonly used software types in the industry include: first, design software for basic heat pump selection; second, SCOP calculators based on standardized procedures such as DIN-EN 14825, which are primarily used for comparing different devices; and third, advanced simulation software. An essential characteristic of heat pumps is that both power output and efficiency depend heavily on boundary conditions. Specifically, they depend on the temperatures in both the source and the heating water, which vary continuously throughout the year. This variability is what makes heat pump selection and comparison so complex. Since some terms are crucial for understanding this topic, let me briefly explain them here. The coefficient of performance, or COP, is a measure of efficiency. A COP of 4.61 means that from 1 kilowatt-hour of electricity, the heat pump can produce 4.61 kilowatt-hours of heat by utilizing environmental energy. It's important to note that the COP depends entirely on the current boundary conditions. This table demonstrates that the COP is not constant. Instead, it depends on both the temperature of the heat source and the heating water, fluctuating throughout the year. In this example, it ranges between 2.62 and 6.14. Even larger COP ranges are common for air source heat pumps, due to varying outside air temperatures, and for high-temperature heating systems. This slide illustrates the concept further. The COP of this modern heat pump ranges from 1.7 to 7.36, demonstrating the significant variability we discussed. Power control means that the heat pump's performance can adapt to current requirements. Therefore, the COP also depends on the operating frequency of the system. This graph shows the fluctuation range of a heat pump's output for a single heating water temperature. You can clearly see that the performance of the heat pump varies significantly across different operating conditions. The following power output specifications are commonly used in the industry. First, the nominal power of a heat pump under standardized boundary conditions. The standard conditions are: for ground source systems, 0 degrees Celsius in the brine and 35 degrees Celsius in the heating water. For water source systems, 10 degrees Celsius in the source water and 35 degrees Celsius in the heating water. And for air source systems, 2 degrees Celsius outside air temperature and 35 degrees Celsius in the heating water. Second, the rated heat output, which is the manufacturer's declared heat output for labeling at standard rating conditions. This applies to the average climatic conditions of -10 degrees Celsius outside and either 55 or 35 degrees Celsius in the heating water. As you can see, the technical data of heat pumps is very extensive. Understanding this complexity is important to appreciate the advantages and disadvantages of different software solutions. After this preparatory overview, let me present the individual software solutions in detail. The goal of design software is straightforward: to select a suitable heat pump for a specific application. Simple design tools compare the required heat load with the heat pump's capacity, then suggest suitable heat pumps. This can be implemented with varying degrees of accuracy. In some cases, calculations are only performed at standard outside temperatures or at a fixed cold temperature, usually -10 degrees Celsius. For example, if a house requires 10 kilowatts of heating, but the heat pump can only produce 8 kilowatts at -10 degrees Celsius, the heat pump would still be considered sufficient with an additional electrical heater. In some cases, The bivalence point is also calculated, which requires more comprehensive heat pump data. The slide shows two curves that intersect exactly at the bivalence point. The bivalence temperature is the outside temperature above which the heat pump can heat the building without any additional energy source, such as a heating element or gas boiler. The blue line shows the required heating output depending on outside temperature. The dashed line represents the maximum possible output of the heat pump. The orange line shows the actual heat pump output, accounting for modulation. The advantage of design software is that you quickly receive suggestions for one or more heat pumps suitable for your project. Generally, only a few technical specifications are required. However, this can also be disadvantageous if the software relies on extrapolation from a small number of data points, making it impossible to verify whether the heat pump will truly be sufficient at very cold temperatures. Here's an example of this problem. If you specify heat pump data at -6 degrees and 2 degrees Celsius, it's quite possible that the heat pump won't reach the required output at -10 or -14 degrees Celsius. With an integrated 9 kilowatt heating element, the total heating output would then be insufficient, resulting in a loss of comfort for the occupants. Additional problems are possible with design software. The design function can be implemented with varying degrees of accuracy. If only the rated output is used, cold source temperatures and achievable flow temperatures, especially for air sources, cannot be adequately represented. If you only use 2 data points and extend the line, you might expect the heat pump to achieve 9 kilowatts even at -14 degrees Celsius. In reality, however, it may only produce 2 kilowatts. It's sometimes unclear to users how these tools actually work. Key questions include: are hot water requirements and off-peak times taken into account? Is sufficient heat pump data available, particularly for cold outside temperatures? Is a check performed to verify whether the heat pump can reach the required temperature? Are heating curves taken into account? A heating curve means that at standard outside temperatures, the heat pump operates at 55 degrees Celsius. But at warmer outside temperatures, it only requires a flow temperature of, for example, 40 degrees Celsius. Heating curves are often not considered, so the bivalence point often deviates from reality. Additionally, design software typically doesn't calculate the seasonal performance factor to assess economic efficiency, and usually provides no information on source dimensioning. With sufficient data, design software is very useful for finding the right heat pump. However, it does not allow for efficiency calculations, which are crucial for economic evaluation. Seasonal performance factor calculations using detailed technical data are possible according to DINEN 14825. SCOP stands for Seasonal Coefficient of Performance, where the COPs are summed up for an entire heating season. These calculations form the basis of the ERP label for comparing heat pumps. They're based on fixed hourly climate values but are limited to 3 locations in Europe: Helsinki, Strasbourg, and Athens. The process involves measuring power and COP at specific temperatures, interpolating intermediate values, and calculating a seasonal performance factor from these measurements. The advantage is that this method can calculate realistic annual performance factors for the specified heating load and comparable location. These calculations also account for reheating and heat pump modulation. Since label calculations are mandatory for manufacturers, a standard exists for data availability, making it possible to compare different heat pumps. The disadvantage is that this method requires more data and involves relatively complex calculations. The result only represents 1 or 2 operating points, namely 55 and possibly 35 degrees Celsius, as well as the climate of Strasbourg or 2 other European cities at the specified demand. Due to the selection of favorable boundary conditions and restriction to limited locations, the result doesn't correspond to a forecast for your specific project. Additionally, simulations for domestic hot water heating are not possible with this method. I've demonstrated that numerous boundary conditions play a role in heat pump systems, including local climate conditions year-round, building characteristics such as heating load and required temperatures, hot water demand, and storage requirements, technical data of the heat pump depending on current requirements, soil conditions and source design, and utility company cutoff times. It is indeed a very complex system requiring comprehensive analysis. When more hot water is required, for example, the geothermal probe cools down more. This cooling leads to lower temperatures in the source, resulting in a lower COP of the heat pump and a worse seasonal performance factor. Simulations can be used to model these complex relationships and their interactions. Heat pump simulation is carried out as follows. Using hourly climate data from the specific location, our WPOPT software, for example, includes every zip code for Germany combined with the seasonal demand of the specific house and the associated detailed technical data of the heat pump. The instantaneous values are summed over the course of the year. Cooling of the ground source is calculated using stored mathematical models. It's possible to consider detailed technical data of the heat pump, tank concepts, and cycling behavior. The advantage is a resulting forecast of the annual performance factor for your specific project. This also enables simple comparison of variance, including the annual performance factor when selecting different heat pumps with different sources. The simulation can consider performance adjustments, check and sum any additional heating requirements hourly, and provide suggestions for source design for ground-coupled heat pumps. You can investigate the impact on operating behavior by varying the source design. In addition, simulations can consider storage concepts, hot water temperatures, the influence of off-peak periods, and other boundary conditions such as room temperature and heating limit temperature. The method is also applicable to large-scale projects with cascades of heat pumps or special cases such as combinations of probes and horizontal absorbers, industrial waste heat, cooling systems, ground-based air preheating, solar thermal systems, and photovoltaic integration. The disadvantage is that simulation is a complex process that requires specific information about the project and extensive data about the heat pump. However, this complexity is necessary to achieve accurate, project-specific results. WPsoft GmbH offers comprehensive, manufacturer-independent and manufacturer-specific calculation tools for heat pump project simulations, as well as simple design tools and seasonal performance factor calculators. According to VDI 4650, we would be happy to support you with our more than 30 years of experience in this field. Thank you for your attention.